Hi, my name is Hannah Lewis, and this is Lab 5, Magnetic Braking with Faraday. To introduce the experiment, first we have the concepts of Faraday's law and Biot-Savart law, and we also have the purpose, which is to explore how Faraday's law relates to time-varying magnetic field to a curly electric field. Then we also have the results, which is that the experimental time for the magnet to fall is 1.02 seconds, and the computational time was 1.205 seconds. Some background on the concepts that are being covered first includes Faraday's law. So Faraday's law relates time-varying magnetic field to a curly electric field without a closed path that is zero. So that current produces a magnetic field which exerts a force on the source of the external magnetic field. Now the equation for this is that the induced EMF is going to be equal to the opposite of the rate of change of the magnetic flux through the circuit. So that's going to be your delta flux magnetic force divided by the change in time. And then just going into what magnetic flux is, it's the measurement of the total magnetic field which passes through a given area, and that is going to be equal to the magnetic field times the area perpendicular to the magnetic field. So in order to look into this concept more, an experiment was completed, and that experiment included dropping a bar magnet down a tube of aluminum foil. So this aluminum foil was at least 1 centimeter thick, so that way there was a conductive surface around the tube that the magnet was falling through. So the magnet would fall, and it was videotaped in order to determine how much time it took for the magnet to go through the entire tube. And from what we know about Faraday's law and magnetic flux, we know that the magnet should fall slower than normal due to an opposing magnetic force compared to gravity. This was seen because the results showed that there was a drop time of 1.021 seconds, which was significantly slower than what we would expect it to be if it was just falling with gravity. This diagram to the right shows how when a magnet is falling through that conductive cylinder, there was going to be the opposing forces acting on the magnet due to the conductive surfaces, which was going to cause the magnet to slowly fall. To check our results also in a more controlled environment, a computational model was created using VPython. So the first step in this was to first create the geometric tube. So we put in the length of 0.3 meters, the width of the foil, which was 0.006 meters, and then the internal radius, which was 0.02 meters. So this was first completed, and then the second step was the properties of the magnet, which included the mass as well as the magnitude of the magnetic dipole moment of our bar magnet. Then outside of that, we had to create a function to calculate the magnetic field of the bar magnet, which was completed on this right side in the code. So we had to first calculate the magnitude of R and then R hat, and then we created the magnetic field using the equations that are already known. And then below that, we had to edit and create a function to calculate the magnetic flux. This was once again using the equations that we know from class. After the magnetic flux and the magnetic field were calculated, these values could then be used in later calculations, which you can see here. So first of all, we have the B field at each ring, and we also have the magnetic force on the magnet, and then finally we have the net force on the magnet total, so F grav plus F magnetic. And then lastly, we were able to create two lines on the graph seen on the right, which shows the magnetic velocity and the bar magnet's position. So on the right, you can see the ending results of this computational model, which includes both the image of the bar magnet following with the two sides of the magnet showed in the north and south poles, as well as the velocity versus time graph, which you can see that the total time in the tube ended up being 1.205 seconds, which was very similar to our experimental result. So now we have our conclusion, which is first, what is the resistance of the conductor was reduced and as close as possible to zero. So how would the dynamic of the falling magnet change? So the braking effect of the magnetic force would increase, which would cause the magnet to no longer fall. And that would be because the gravitational force would be equal to the magnetic braking force. So there would be a net zero force on the magnet. Then finally, what if the holes or slots were cut into the tube? How would this affect the ring currents? So the braking strength would decrease and cause the magnet to fall slower because the flow of the current through the rings of the tube would be disrupted. Thank you for watching. Have a great day.